the rest part of the trig unit. And this is now where we start to use, or we no longer are going to be using calculators because we don't need them. Okay. This week I'm looking at getting through sections 13.2 and 13.3, and it usually takes a good solid 4 to 5 days to get through all of that without too much of a hassle. I don't see us starting 13.4. Maybe a small amount of it come Friday if we get to it. If not, not that big of a deal. I probably don't see a quiz in any of this week, so there's that. Not this week. I don't think it'll be this week at all. I really don't. The way that I break some stuff out. So what we're going to do here today is we're going to talk about what does it mean to, or the button that's on your calculator that talks about radian. We're going to talk about that. We're going to talk about areas of sectors, arc length, things that you've done before in geometry, and we're also going to talk about how you position, how do you talk and work with angles. So when we start looking at this idea of working with angles, excuse me, we have what are called angles in standard position. Angles in what's called standard position. And angles that are, oops, all over the place. Angles that we're talking about what are in standard position. We start our angles, change the color here. This is what we call we start our zero them out on the x-axis on the right side. We call that the zero. Or better yet, the initial side. Oops. The initial side is right there. And then they move to what's called the terminal side. The initial side starts at 0, and it goes to whatever, 0 degrees for right now. And it goes to whatever is out here. So let's say that this is maybe 110. I'm making something up. It's going to be it has to be more than 90 degrees because 90 degrees is your vertical. 180 is your flat. And we'll go through all that stuff here in a minute. Excuse me. So as we go around, we have 0, 180, 360, 90, and 270. We'll just leave it for that right now. You can have your angles when you talk about them. When you start at your 0 line, angles go counterclockwise when they're positive. So positive angles. They go counterclockwise. And then negative angles, which is a thing, go clockwise. Negative angles just mean you're going the other direction. So if I said negative 60 degrees, negative 60 degrees just means I move down here 60 degrees. That's all that means. Right? That's all that means. It's just direction. So it is completely possible. I know we've told you this many times before. You can't have a negative angle. The negative angle just means it's direction. Yes, sir. Oh, you've never seen my angle sign before? Yeah. Okay. I grew up back in my day. We talked about angles, and you had the angle symbol. Kids use that stuff. What happened? Devin, are you messing with my board? So the angle symbols a lot of times looked kind of like a less than symbol. My teachers in geometry and algebra and all that put an arc in them. Okay, they put an arc in them, and the reason why they have an arc in there because on the unit circle, which we'll talk about here, angles create a bit of an arc, and that's where that comes from. Okay. Yes, ma'am. Oh, did it all go away? Yeah. Oh, look at that. Yeah, look at that. So positive angles. Positive angles go that direction, and then negative. Just a little bit. So it's clockwise or counterclockwise. One of the things I want us to get accustomed to doing and working with is when we are working with the angles, is that whenever we draw an angle, I always want to see how far it is off of an x-axis. There's a reason why I'm starting to put that into your minds now. So a minute ago we did that 110 degrees. If I wanted to draw what 110 degrees looks like, we knew it goes past 90 degrees, it ends here. How far is that from the x-axis? 70, okay? When I did the negative example, I did what was it, negative 60, I think? Is that right? So if I did the example of negative 60 degrees, when I draw that, we move down negative 60. Well, how far is it off from the x-axis? 60 degrees off. There's a reason why I'm doing this now. It's because in a couple of days, when we talk about what are called reference angles, you'll get used to knowing what that meant. Because I'm having you do a little bit of that work now, so you're not just bombarded with all this crazy information later. It's foreshadow. So, excuse me. Oh, I'm sorry. As I was saying, this was 0, 360 degrees all the way around. This was 180. Here was 90 and 270. Where the angle stopped, remember we called that the terminal side? If angles share the same terminal side, they're called co-terminal. Let me bring this over here. We'll use this example here. This is a good one. So angles that share a terminal side are called co-terminal. So if I'm looking at 110 degrees, what would I have to add or subtract to 110 degrees to wind up back at 110 degrees? Well, if I add 180 to it, don't I just wind up down here? I have to add 360 to it. Everybody see that? Ready? Better? You're gonna be good. How many degrees was that? How many degrees do I need to get back to 110? Another 110. How many degrees did I just go? 470. 470 degrees has the same ending position, same terminal side as 110 degrees. Yep. Correct. And that's the idea. You can keep adding 360 degrees, you wind up the same spot you are. You know, if I say stand up and turn 360, aren't you always going to face the way you first were facing? If you're doing it correctly, or if you don't get dizzy and fall over. Okay. Now, what if I went the other direction? What if I went negative? Careful. If I went negative 360, if I go negative 360, I wind up back there. So if I want to wind up at 110, I go, here's negative 180. And how many degrees up did I have to go? So what's 70 more than 180? 250. So the coterminal angle would be negative 250 is also that. That's all you're doing. And the trick here is, all you're doing is adding and subtracting 360 degrees. And you will wind up, I know. It's crazy, okay? All you're doing is adding and subtracting 360 degrees to get you back in the same spot that you were. Now, what becomes a little bit weird with this is if your first angle is more than 360 degrees to start with. The general rule for working with what are called positive and negative coterminal angles Really, the only rule you want to be with is that your original angle, is within, can't write, within 1 revolution. Negative 250 and 470 are coterminal. The 70-degree part that we got here, this was just telling me how far I was off the x-axis at the original 110, because that means I knew how much I had to add to go back up to it, or I knew how much I had to subtract to get down from it. So we're using that. We always are going to bounce whatever angles we place. We're always going to bounce them off of the x-axis. We're always going to measure how far they are from the x-axis. Like I was saying, there's a reason that we're flying, flutter. There's a reason why I'm doing that, and I'm setting it up a couple days ahead of when we really need to. It just makes it a little bit easier. So, excuse me, if we start with an angle that is greater than 360, all we do is just back it out until you get within 1 revolution. Then you back it out again, and then there's your negative. Super easy to work. Okay. For example, if I take 700 degrees, does everybody agree 700 degrees is more than 360 degrees? Okay. So let me put this on a clean line. What? All right. Well, we can try. So if I want to do a 700 degrees, and I want to do a 1 positive and 1 negative coterminal of this, first thing I do is figure out where do I land. 700 degrees is positive, so I'm going to go counterclockwise. If I go 1 revolution is how much? 360. Then if I go to here, it's 540. If I did 2 full revolutions, it would have been how much? 720, which means how far off am I from here? 20. Everybody okay with that? You're just counting by 360s. Okay, you're just counting by 360s. Bless you! Okay. Now, since 700 degrees is more than 1 revolution, I'm going to subtract 360, because if I subtract 360 from that, I will be within 1 revolution. 700 subtract 360 gives you what, 340? So here is your positive coterminal angle. Has the same distance off the x-axis, it's 20 degrees off. And if I do that one more time, what is my negative coterminal angle? Negative 20. And there's my negative coterminal angle. Because all I had to do is move down 20 degrees. When you're talking about finding what are called positive and negative coterminal angles, that's all you're doing. You're adding and subtracting 360 degrees. Okay. The reason why we use these is because later on we're going to work with what are called reference angles, and reference angles are always going to be set within 1 revolution. And if we know how to figure out where they are in 1 revolution, trig's easier. Speaking of trig, this is where things get kind of radical. If you watch it on your own, I'm not going to take valuable class time to watch the movie Rad. So let's talk about this. Radians. Radian measure comes from circumference. Radian measure comes from circumference. You might want to draw this a little bit larger so you have a little bit of space. I forgot to tell you that. If you have, or unless you've got really good handwriting lip. Now, if you start thinking about this idea of what a circle looks like, How many degrees does it take you to get around a circle? Okay. So here's 0. Here's 360 when I finish. What's half of 360? What's half of that? Now, do you guys agree that the 90 and then the point down here are just vertical from one another? Which means all you have to do is add 180 degrees from it, and you get 270. Good. Now, when you dealt with circumference, do you remember what the formula for circumference was? 2 pi r. Very good. Now, if I say that my radius here is 1, what's the circumference of that circle? 2 pi. So in order to get all the way around the circle, I have to go 2 pi. I still start at 0, but I end at 2 pi. Well, if I go halfway, how far do I go? Pi. What's half of pi? 1/2 pi. Or pi over 2. If I add 1/2 and a whole, I get 1/2, correct? But we don't like mixed numbers, we like top heavy. So 1/2 would be 3 over 2. You okay with that? What I've done here is we've broken it into 4 parts. 0, 1/2, 2 halves, 3 halves, and 4 halves going around the circle. You all right with that? What's half of 90? 45, good. So if that's 45, then if I put 45 here, what's 90 plus 45? Add 45 to that, you're at 180. Add 45 to that, you're at 225. Add 45 to that, you're at 270. Add 45 to that, and you're at 315. See where I'm going with that? Now, what's half of a half? A fourth. So if 90 is at pi over 2, 45 would be at pi over 4. So as you break this down, we went from 0, 1/4, 2/4, 3/4. 4/4 is my whole. This is 5/4. 6/4 is here at the 3 pi over 2 because it simplifies. Add a fourth to 6/4 and you get 7/4. I know. And then lastly, it would be at 8/4, which is the same thing as 2. Okay. Not too bad so far. Notice we just broke it down into quarters. 1, 2, 3, 4, 5, 6, 7, 8. 8 quarters going all the way around. Okay. Now, what is 1/3 of 90? 30. Okay. 1/3 of 90 is 30. If I add 30 to that, what do I get? 30, 60, 90, then what? 120, 150, 180, 210, 240, 270, 300, 330. We okay with that? All I did was just count by 30 degrees. All I did was count 30 degrees going all the way around. Okay? I count by 30 degrees going all the way around. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. You get all the way around the circle, just counting by 30s. Okay? Now, if 90 was pi over 2, 30 is 1/3 of 90. What's 1/3 of a half? A sixth. So at 30 degrees, I have pi over 6. 1/6, 2/6, 3/6 is 1/2, 4/6, 2/3, 4/6, 5/6, 6/6 is my whole, 7/6, 8/6, which is 4 pi over 3, 9/6, which is 3 over 2, 10/6 is 5 pi over 3, 10/6, then it becomes 11/6, because then you go up 30 degrees, you're at 12/6, which is 2. There isn't any more. Okay? There isn't any more for algebra 2. There will be more in pre-calc. Because then you get half angles and double angles and stuff like that. Because in pre-calc, you'll talk about pi over 12. You'll talk about 75 degrees, things like that. But it's not too. That's where. This is the main reason why we spend so much time in geometry with your special right triangles. Notice, all I did was just count that entire unit circles, what that's called, because of your 30, 60, 90, and your 45, 45, 90 triangles. Those two setups, those ratios of sides, will help you build all the sine, cosine, and tangent values of every single thing on there. And quite honestly, you never have to memorize any of this. Because if you know that 90 is half, what's half of a half? A fourth. What's a third of a half? A sixth. 30, 60, 1/6, 2/6, 3/6, and you can build everything out by going through the fractions. Now, what we just did there is we converted all the special angles, your 30, 60, 90s, your 45, 45, 90s, into what are called radians. Radian measure is how much of the circle are you of the circumference. There is a formula to convert from degrees to radians, and there's a formula to go from radians to degrees. Degrees have degree symbols. Radians have pi. Okay? Radians have pi. Now, in order to convert back and forth, we do this. I want to go from degrees to radian. If I want to go from degrees to radian, basically I'm doing this. Angle over 180 and slap a pi next to it. So earlier we had that one, we had what, 110 I think? What's that, I'm sorry? Yep. Because what happens with the fraction, I'm going to show you what happens here. You can do it, you can write it a couple different ways. If we go back to that example where we had that 110 degrees, if I want to write that in terms of radians, all I'm going to do is go 110 over 180 and slap a pi next to it. And I simplify that fraction. 110 over 180 simplifies to be what? 11/18. Yep. So your answer would be 11 over 18 pi. Or, like you were just about asking, you can write it like this, 11 pi over 18. Either one of those is fine. Because when you're multiplying things together, when you have stuff in the numerator, it's just multiplying the numerator straight across. You'll probably see it written more often as 11 pi over 18, as opposed to 11 over 18 times pi. I think that's where you're about to ask me. Now, if I want to go the other direction, if I want to go radians to degree, I'm no longer multiplying by pi and dividing by 180. I do the opposite, or the reciprocal of it. I multiply by 180 and divide by pi. So if I have, let's say, 7 pi over 8, and I want to convert that to degrees. What's that? Oh, sorry, I said it. So here I would do, I take the radian, whatever the radian is, times 180 divided by pi. He left. Did he leave? Devin's still there. Sorry, Devin. For some reason, it looked like you left. No. It was all messed up, Devin. I'm sorry. Don't hate me. Anyway, so if I have 7 pi over 8, what I'm doing is I'm going to multiply that by 180 and divide it by pi. Because what's pi divided by pi? 1. That's how you're able to get that's basically you're just unit canceling. Okay. 180 and 8 are both even. Would that be 4 and 90? They're both even still, aren't they? 2 and 45. So let's see, 7 times 45 would be what? 315? Well, it's 7 over 2, but I said 7 times 45. Oh, okay. So 7 times 45 is what, 315? So your answer would be 315 over 2 degrees, whatever that is. Excuse me, so that's what, 167.5? Is that right? Yes, ma'am. That's fine. That's fine. Because you probably, I probably won't be using any calculators for any of this. And to be honest with you, converting back and forth between radians to degrees, there's really not. I think that the first couple of days, you guys will probably do that a lot because you know what it's like to work with degrees, and you're not used to seeing radians yet. So a lot of times in your mind, you'll be converting a lot. I'm gonna try and let you do that for a little bit, but then I'm gonna kind of say, hey, stop doing that. Trust yourself and understand how things work with the unit circle, because as we get into it, it just makes everything so much easier to do. Excuse me. So that's how we go back and forth on those. One of the other things with the radians, and we didn't do an example of this yet, that I wanted to explain at first was, how do I do a coterminal angles with radians? If I want to do coterminal with radians, what's that? Yeah, it's when you're doing with radians. Let's say we have, we'll make it easy. Let's say it's 13 pi over 4. Is a lot of times, again, you're going to start seeing non-mixed numbers. Okay, and I know that I said that mixed numbers are just stupid, but there is a time and a place for them, and this is probably the one time and place that mixed numbers aren't so bad. 4 goes into 13 how many times? How many are left over? So this is the same thing as saying 3 1/4 pi. You okay with that? The reason why I say that working with mixed numbers with radians is kind of a nice thing to do is because as you count 1 little, 2 little, 3 little pies, quarter. There's my angle. What I'm looking at here, guys, is I can count by pi. The reason that I can do that is because here's 0, here's 1 pi, here's 2 pi, and I know I had to go around 3 1/4. Okay? A quarter is 45 degrees. If it was a half, it would have been on the axis. Okay? So if I'm looking at this, I went 3 pi. Bye, David! I'll have the homework online. I went down 3, and then how far did I drop below that third pi? A fourth. I moved down pi over 4 there. Okay? So this, I know it's possessed. So when we do, oops, let me just shut this off. Maybe it's doing that. Now, you guys agree that this is more than one revolution? So since I'm beyond one revolution, I just have to back out 360 degrees. But in this case, I'm backing out how much pi? 2 pi. If I back out 2 pi from 3 1/4 pi, how much do I have? 1 1/4 pi. So my coterminal angle here is 1 pi plus 1/4, so that's 5 pi over 4. Yes, ma'am. The reason that because I am beyond one revolution. 2 pi is one full revolution. So I went, I'm sorry, I drew that the wrong way. 2 pi, I go around, there's 2 pi, and I went back around 3 1/4. So I'm beyond 360 degrees. So I know that like we said earlier, whenever you're doing positive and negative coterminals, you always want to get within 1 pi first. No, because what I did here is, this is 1 1/4 pi. I took 3 and I subtract 2 and I left with 1 1/4, and I just write it back as a mixed number. No, I'm sorry, not mixed number, as an improper. Cool. What's 4 times 1 plus 1?
Wait, so should it be drawn under it then, or is it total?
I just drew the positive one. I haven't done the negative one yet. Okay. Yeah. We knew that this was 3 1/4. 1 pi, 2 pi, 3 pi, quarter. Now, what Maggie was just asking was, we did the positive. If I do the negative, I come out here, I'm still 1/4 away from a whole negatively. Perfect. It's negative. The negative would be negative 3 pi over 4. Because the whole would be negative pi, subtract the quarter, because that's how far you are off of it. It just takes a little getting used to. It is relatively simple. It just looks kind of weird. Okay. Yeah, and you can really mess around and say, hey, what's 900 degrees? You start with 900, you really have to loop it around, and then you have to start backing it out. And it's just a matter of counting. It's just a matter of counting. I'm sorry, what's that? Subtract from what? Oh, because I went negative direction. If I went from 0 to here, it would have been negative pi. I just backed out a 4th because that was how far I was from the axis. That's the main idea of always figuring out how, guys, that's the main idea by always figuring out how far you are bounced off an x-axis, whether you're above it or below it. That way you can get those reference points. That's the trick. If we can get those reference things, everything is so quick. Okay? Now, one of the things that you actually did last year in geometry all dealt with radians. You just didn't know that's what you were doing. For example, do you remember this? You remember arc length? When you did arc length, you had some central angle, a radius, and it was how far you were on the circumference. Now, I know that I wrote mine out was this. It was the arc length was your central angle over 360 times 2 pi r. Remember that? But I think most of the time you guys simplified it because how many times does 2 go into 360? So a lot of times you wrote it as this. Angle over 180 times pi times your radius. Now, isn't that just radian? That's just radian. What you were doing last year is you were working with arc length by putting it in terms of radians. You did that all last year. You didn't even realize what you were doing. Okay. What you do here is this arc length, what they change it up now is at this portion here, arc length now, in this text, they use the letter S, and it's going to equal theta times your radius. I don't know why they use S. It's kind of silly. Now, this value of theta, yeah, circle. Circle gets the square. This theta value is your angle in radians. So theta stands for angle over 180 times pi. You did this last year, you just didn't know that's what you did. Same thing goes for when you had to find sector. Remember the area of the sector? Remember the area of the sector? You had the area of the sector was dependent upon your angle. So it was your angle over 360 times pi r squared. What's that? It sounds about right. But now they changed the area of the sector one up, and I'm going to screw this up. I want to make sure I write it down. Yeah, I always forget it. It's 1/2. Oops. Or theta is radians. Okay. So the reason why they put the 1/2 in there is because if you're converting to radian, it's central angle, it's your angle over 180. But when you're talking about sector, you're looking at the angle in terms of the entire circle. So that's why they have to put the 1/2 times the 1 over 180 to get over 360. That's where this all comes from. So again, last year you did this. You did angle over 360 times pi r squared, and that gave you the area of the sector. Here, they're just saying convert it to radians and multiply it by 1/2 r squared. Okay. And it does the exact same thing. Yes, sir? We're not using calculators. And honestly, the calculator will, even if you're using radian in the calculator, it's going to be for the oddball ones. What we're going to look at mainly is going to be all of our specials and what are called on the quadrantals. And those you will not need a calculator for whatsoever, because you know the ratios of the sides of 30, 60, 90s, and you know the ratios of the sides of the 45, 45. Everything that we're going to do in here will be built off of one of those angles as a reference. Okay, every single one of them. And if you really think about it, you have 30, 45, and 90, and 60. So there's 4 angles. If you understand how to work with 4 angles, no matter what I give you, it's going to be some variance of those 4 angles. And you just have to watch your signs, your SIGN, see which one is positive and negative. It becomes super simple, and this is so visual. For those of you guys that like to draw pictures and diagrams and map out where things are going to go, everything that we do for the next couple of weeks is so visual, and it's so cool how it works. Okay, I love trig. It's great. Trying to instill some excitement in some of this. I try to be nice and show cool things. Quadrantals are your verticals, horizontals. Here's what I got. Where's my book? Okay. You're doing basically drawing the angle so you get the idea of where it lands, how far is it off the x-axis, positive and negative coterminal angles, spinning it back and forth. You've got a couple of converting from degrees to radians, a couple from radians to degrees, and a couple arc length and sectors. It seems like it's a lot, but honestly, as you get going into this might take 15 minutes. It really is pretty quick. Yes, ma'am. Yeah. It's 1/2 radius squared theta. Theta is in radians, so it's basically it's 1/2 1 over 180 times your angle times pi r squared. It's basically this value here is theta, because theta goes in radians. Make sense? It's super easy. I know you guys will be fine with it. Reminds me to post this. What's up? Yeah, there's a couple of them in there. It's just formula. No, you did that last year, but this is a different. It's a different way of writing it.